In 2001, researchers Jürgen Schmidhuber, Sepp Hochreiter, and Joshua Bengio stated clearly, random guessing cannot be viewed as a reasonable learning algorithm. Today, that skepticism persists in how we handle post-training for large language models. The consensus is that adapting a pre-trained model to specific tasks requires complex search methods like PPO or GRPO. These are reinforcement learning algorithms that update model weights in jagged sequential steps based on a reward signal. But a new approach called RandOpt challenges this requirement. RandOpt simply guesses thousands of random parameter perturbations in parallel, evaluates them on a small dataset, and ensembles the predictions of the top performers. This bar chart compares Qwen 2.5 3B model performance on reasoning benchmarks like GSM-8K and Countdown. GSM-8K is a benchmark of grade school math word problems, and Countdown is a numbers game requiring exact arithmetic. On the Countdown task, RandOpt reaches 87.1% accuracy, matching or exceeding the sequential updates of PPO and GRPO. Because RandOpt simply tests parallel guesses, its training steps operate in O1 time. O1 indicates constant training time regardless of the number of evaluations, while OT means time scales linearly with a long chain of sequential update steps. When deployed on a cluster of 200 GPUs, RandOpt evaluated 2,000 parallel guesses and trained the 7 billion parameter ALMO3 instruction model on the Countdown task in just 3.2 minutes. The success of a guess and check strategy suggests that the valid solutions to these tasks are far more abundant than we previously assumed. To understand how random perturbations can match sophisticated optimization, we have to look at the actual shape of the space surrounding a pre-trained model's weights. We can measure this environment using solution density. This is the statistical probability that a random local perturbation to the weights will actually improve the base model's performance by a specific margin. These 2D accuracy landscapes show Qwen 2.5 weight spaces. Red indicates accuracy gains, blue is degraded performance. At 0.5 billion parameters, pre-trained weights sit on an isolated peak surrounded by blue. Scaled to 32 billion, the topography flips, inhabiting a dense red basin of task experts. Tracking model scale against Countdown accuracy reveals a sharp inflection point at 1.5 billion parameters, the exact threshold where weight space becomes dense enough for random guessing to work. But this density requires pre-training. Applying RandOpt from scratch yields near zero performance. Increasing the scale of a model transforms the geometry of its weight space. The initialization point moves from an isolated peak of accuracy into a dense, high-performing environment, a neural thicket.
If the local landscape is full of improvements, are these perturbations uniform generalists that improve everything, or narrow specialists that trade one skill for another? This chart tracks the performance spectra of 100 random weight perturbations across math, programming, writing, and chemistry. Instead of flat lines, we see a jagged distribution. A single perturbation might excel at a coding task like MBPP, but perform poorly on ROC stories. We quantify this extreme specialization using spectral discordance, a metric measuring how orthogonal or uncorrelated these task rankings are across the different perturbations. This graph tracks spectral discordance across model scales, showing that the metric increases monotonically from 0.5 billion to 32 billion parameters. The larger the model, the more disjoint and specialized its surrounding local experts become. In this RGB composite column, performance on 3 tasks is mapped to red, green, and blue channels. The heavily modeled, multicolored patches in larger models prove that experts for different tasks occupy distinct, non-overlapping regions of the weight space. Because these perturbations act as narrow specialists, no single random guess solves every task. The system relies on majority vote ensembling to aggregate their individual strengths into a cohesive, high-performing output. To isolate the mechanism behind thickets, we use a simple autoregressive model trained entirely on 1D signals, like sinusoids, sawtooths, and square waves. We prompt the model with a short observed context of a linear signal and test whether random weight perturbations can accurately predict the remaining ground truth. This image shows the predictions of a model with zero pre-training. The solid black line of the base model diverges immediately from the dashed blue ground truth. Without prior exposure to signal patterns, the model is trapped at its initialization state. Random weight perturbations yield no functional diversity,
making the search for the correct linear path impossible. This image shows a model pre-trained exclusively on linear signals. Here, the base model perfectly follows the ground truth entirely on its own, leaving no room for random perturbations to offer any further improvement. But pre-training on a diverse mixture of signal distributions changes everything. The random perturbations branch into a massive gray spray of potential continuations. We simply sample from that latent library, yielding the red top K-lines that successfully trace the linear ground truth. Thickets do not appear by accident. They are the direct geometric consequence of pre-training on mixed, multitask distributions, arranging an entire library of specific experts in the immediate radial periphery of the base weights. A skeptical observer might ask if these random perturbations are actually improving the model's logic, or just fixing shallow surface-level behaviors, like ensuring an output matches a specific JSON format. This stacked horizontal bar chart breaks down the accuracy gains on the GSM 8K math benchmark using the 3 billion parameter Quen model, comparing the base model against GRPO and a 50-pass RandOpt ensemble. 19% of RandOpt's total gain comes from what we call a format thicket. This occurs when the base model originally solved the math problem correctly, but the strict answer checker failed it until a random perturbation fixed the output syntax. However, an additional 12.3% of the gain comes from a genuine reasoning thicket. In these cases, the base model completely failed the logic of the problem, and the random perturbation corrected the actual mathematical method. These reasoning gains persist even when testing RandOpt on fully transparent open-source models like OLM03. Because the entire training pipeline of OLM03 is public, we know these gains are not the result of bypassing hidden safety constraints or sandbagged capabilities. The neural thicket is multi-layered. It houses simple formatting experts just a short distance away from specialists capable of entirely new logical deductions. The data requires a shift in how we conceptualize the outcome of a training run. A pre-trained model is not a single fixed point in weight space, but rather the center of a dense distribution of specialized behaviors. Under this framework, post-training is no longer an act of forcing the network to learn a complex new skill step by step. Instead, it becomes an exercise in selection, identifying and ensembling the experts that already exist nearby. Because this selection process can happen via parallel random guesses, it allows for decentralized adaptation. Compute nodes can search the thicket independently without the massive communication overhead required by traditional gradient updates. Once a network achieves a strong pre-training representation, adaptation stops being an uphill climb. The geometric density of the weight space does the heavy lifting. In the dense environment of modern large language models, the oldest and simplest algorithm, guess and check, is highly competitive with the state of the art.